next topic is conservative forces versus non-conservative forces. So we have just discussed in conservative forces, work done is independent of the path. So no matter what path you take, as long as the initial and the final points are the same, work done is always the same. But in case of non-conservative forces, work done clearly depends on the path. So examples of conservative forces which we already discussed, number one was the gravitational force. Number two, we have spring force. Three, electric force, and then we have magnetic forces. So all these forces are considered conservative. On the other hand, what are the examples of non-conservative forces? So you need to remember, first is the friction. Second, we have air resistance. Third, most importantly, applied force. So if you are pulling or pushing an object, that applied force is also non-conservative. And fourth would be tension. So these are some examples of non-conservative forces. Now let me try to explain this using a diagram. So imagine we have a ball over here. Let's say this is the initial point and it is going towards the final position. Case 1, the ball is going in a straight line along this red arrow. And let's say the work done by the ball while it is following this path is, let's say, W1. So this is case 1. Case number 2, the ball is traveling from the initial to the final point but along a different path. So have a look. The path becomes irregular. So the initial and final points are the same, but the path taken is definitely different. So in this case too, let's say the work done is W2. Now let us consider the third path. The object reaches the final position and let's say the work done in case 3 is W3. So according to the definition, if the forces involved are conservative, all the work done will be equal. So work done is independent of the path. That is the definition of conservative. On the other hand, if the forces involved are non-conservative, then the work done will of course be different. So W1 is not equal to W2, not equal to W3. So in the exam questions, it will be very crucial for us to figure out what is the work done by a particular conservative force. And that is the next title, work done by conservative force. So the formula is simple. WC stands for the work done by the conservative force. Delta U is the change in the potential energy. Change in potential energy is final minus initial. So if we combine the expressions, we will get WC, work done by the conservative force, equals to negative delta U, which will also be equal to initial energy minus final energy. And why we have placed initial in the front? Because of the minus sign. So let's say if the question asks us to find the work done by the gravitational force, so the formula becomes work done by the gravitational force, which is mg. Work done by mg will be equal to negative of change in the gravitational potential energy. So the formula becomes this, and GPE initial minus GPE final will give us the work done by the gravitational force. After this, let us consider spring forces, which are also conservative. So work done by spring forces will be equal to negative of change in the elastic potential energy. So let's write work done by the spring force will be negative delta EPE, which is equal to the initial elastic potential energy minus the final elastic potential energy. And now let us try to solve a question based on these principles. So here we have an inclined plane on which a box is kept. So the question is, what is the work done by the gravitational force acting on the box as it moves up the incline from point A to point B? Now the question has specified that we need to find the work done only by the gravitational force which is acting downwards. Now there are two ways to solve this question. Method number one, we are going to use the basic formula, work done by a conservative force is equal to negative of change in the potential energy. In this case, the force is gravitational, so we will write down the formula, work done by this gravitational force mg will be equal to negative of the change in the gravitational potential energy, which can then be written as GPE initial minus GPE final. Initially, the box is at point A, and since the point A is on the ground, we can assume the gravitational potential energy of the box at the point A to be 0. So initial GPE will be 0. And finally, the box reaches point B. There the formula for GPE we can use mgh, where the height is 1 meters, as you can see in the diagram. So over here, we will write initial GPE is 0. Final GPE is mg into 1. And if we simplify this, we will get negative 20 as the answer, because the mass of the object is 2 and g is 10. So work done by the gravitational force as it is going from A to B will be negative 20 newtons. So this is the first way of solving this. Now the second method, we are going to use the basic formula for work done, which is F into S into cos theta. Now we also know work done can be written like this. Work done is the product of force with component of displacement along the force. Now, if you analyze this image, although the box is going from A to B, that is the overall displacement AB. But what is the component of displacement along the force? Now, the force mg is vertical, it is along the y-axis. So, we have to find the y component of AB, which will be CB. Now, if we understand the total displacement, the object is going from A to B in a straight line, but in component terms, we can say that the object is going from A to C along the x-axis, and then the box goes from C to B along the y-axis. Now, since we have to find the component of displacement along the force, that component is BC, which is 1 meters. And then we can write this expression as force is mg and the component of displacement is CB. And why we have put a negative sign in front of this formula is because the force mg and the displacement are in opposite direction. So if you analyze this image, mg is downwards, the object is going from C to B along the y-axis, so CB is up, mg is down, and that is why we have put a negative sign. And that's it. Let's put the values in. M is 2, G is 10, and CB is 1 meter. So if we simplify, we will get negative 20 newtons as the answer. So in an exam scenario, depending on which method you prefer, you can use any method. But generally, this method 1 is preferred because there we don't have to deal with any components. All right, so now back to the logic. Whenever we are applying the conservation of mechanical energy, we need to be careful about certain conditions which needs to be satisfied. Condition number 1, which we discussed, the system should be isolated, which means the net force acting on the system should be 0. And number 2, all the forces acting on it should be conservative, which means forces like friction, air resistance, applied force should not be there. So if a non-conservative force like friction acts on the system is going to lose energy. For example, in the form of thermal energy. So in that case, mechanical energy will not be conserved. So while solving questions, we need to be careful about the presence or absence of non-conservative forces. So again, consider we have a block which is kept on an inclined plane and it is sliding down this incline and finally reaching the bottom of the incline at the final velocity v. So according to the law of conservation of mechanical energy, initial energy will be equal to the final energy. But do remember, you have to apply this equation only if friction is absent. So let's see, use mechanical, remember this as a rule. So use mechanical energy conservation only if conservative forces are present. If non-conservative forces are present, for example, friction, in those cases, the approach is a little tricky to apply. But in most cases, we can consider this as a rule. So mechanical energy conservation applicable only if conservative forces are present. Now imagine if this inclined plane surface is rough, so it has friction. So if the surface is rough and has friction, it is better not to apply the energy conservation. As I explained earlier, it is a little tricky to apply it. The easier way out is to use the work energy principle. So for the rough surfaces, it is better to use the work energy principle. Now let us understand this by taking a specific example of a ball bouncing off the ground. So imagine there is a ball kept at a height h above the ground and it is released from rest. So as we release the ball is going to fall down towards the ground. And let's say we label the topmost point as A and the point where the ball hits the ground, that is point B. Now, when the ball hits the ground, it is going to bounce back up. And of course, after the bounce, the ball is going to follow the same line and it is going to go up. But just for the sake of clarity, we will draw a separate line for after the bounce. So after the bounce, let's say the ball is going up and it reaches the highest point. And let's say that point is labeled as point C. So just to clarify, we have drawn two separate lines. The first dotted line is for when the ball is falling down, and the second dotted line is for the ball when it is going up. We have drawn separate lines just for the sake of understanding. Please know that the ball is going to go down and bouncing back up within the same straight line. So to sum up, the situation which we are considering here is a ball is released from point A, it rebounds on the ground at point B, and then it goes up from B up till the maximum height C. So now we have to consider, is the law of mechanical energy conservation applicable here or not? So how do we analyze it? So we need to observe the different forces acting on the object. Remember the concept, if conservative forces are acting, then we can apply the mechanical energy conservation very easily. If we have a non-conservative force present, then mechanical energy conservation cannot be applied. So over here, the ball is going to bounce at the point B. At the point B, ground pushes the ball back up with a normal reaction force. Let us understand this point in a little more detail. So imagine we have the ball, it is coming towards the ground. The moment it hits the ground, so we are considering the point B when the ball has made an impact with the ground. So over here, I have drawn the ball and the ground separately just to draw the separate free body diagrams for the ball and the ground. So let me repeat, the situation which we are considering is when the ball is hitting the ground. So the ball is in contact with the ground. And over here, we are drawing the separate free body diagrams of the ball and the ground when the ball and the ground are in contact with each other. So what are the different forces acting on the ball? The first force is the weight of the object, which is acting downwards, mg. Now let us summarize the situation. We had a ball which was released from rest. It is going to speed up. It is going to hit the ground at the point B. Now, since the ball is hitting the ground, which means the ball is providing a force to the ground in the downward direction, which we can show over here. So this N is the normal reaction, or rather the force provided by the ball to the ground in the downward direction. And according to the Newton's third law, if you remember, forces are always in pair. So if the ball is pushing the ground downwards, so the ground will also push the ball upwards. And according to the Newton's third law, the magnitude of those two forces will be the same. Direction is opposite, and forces always act on different objects. So one force is acting on the ball, the other force completing the pair is acting on the ground. So we conclude that the ball is being acted upon by a force which is the normal reaction. Now, normal reaction is a non-conservative force, and we already know the principle that we can use the mechanical energy conservation easily if only conservative forces are present. Now, since we have a non-conservative force, so mechanical energy cannot be conserved. So let us summarize. Consider all these points. If the object is going from A to B, or the object is going from B to C, or we consider the entire motion starting from A all the way till the final point. So in these motion, we cannot apply mechanical energy conservation because of the presence of normal reaction, as it is a non-conservative force. But there is a trick which we can use to apply the mechanical energy conservation in such cases where the ball is bouncing off the ground. How do we do that? So look at the same diagram. So the ball was released from rest at the point A. It falls towards the ground. It is going to speed up, but just before hitting the ground, let us draw the position of the ball. So let's say the ball is at point P when it is just about to hit the ground. So P is the point just before impact with the ground. Afterwards, the ball is going to collide with the ground at the point B, and just after the bounce, we can draw the position of the ball over here at the point Q. So Q is the point just after impact with the ground. And we can also see the direction of velocities at the point P and Q. So just before impact with the ground, the ball is moving downward, and just after impact with the ground, the ball is going upwards. And now if we consider these points, we consider the motion of the ball from A to the point P. P is the point just before impact with the ground, and consider the motion of the ball from Q to C, which means just after impact with the ground until it reaches the maximum height C. So when the ball is doing motion from A to P or Q to C, only the gravitational force is acting on the object. So mechanical energy will be conserved, as gravitational force is the conservative force. And using the law of mechanical energy conservation, now we can write that the total energy of the ball at the point A will be equal to the total energy of the ball at the point P. Similarly, the energy of the ball at Q will be equal to energy of the ball at C. But total energy of the ball at A cannot be equal to total energy of the ball at C. So EA is not equal to EC. And why they are not equal? Because if we are considering the motion of the ball from A to C, the ball is going to hit the ground, because of which the ground is going to provide an upward normal reaction to the ball, and normal reaction is a non-conservative force, and that is why EA and EC are not equal. And let us summarize the entire situation. Whenever the ball is bouncing off the ground, so from A to P or from Q to C, we can apply the mechanical energy conservation like we have shown here. But if you consider the overall motion from A to C or A to B or B to C, so considering all these motion types, mechanical energy will not be conserved because in these motions, the ground comes into the picture and the ground gives a normal reaction to the ball in the upward direction. Normal reaction is a non-conservative force, hence the mechanical energy is not conserved. Now let us solve a question based on this.